Okay, Chapter 5, Section 2. We're going to talk about machines. So what is a machine? So machine is any device that makes work easier. So remember, what is work? Well, it's the ability to use energy. Remember that in order for work to be done, you have to have energy being used in the same direction of the force being applied to it. So machines can be simple, or they can be somewhat complex. So some simple machines that we might think of are like scissors, knives, doorknobs, anything that allows us to do something that is a little bit easier than if we had to do it the other way. So if a machine can make work easier by increasing the force that you can apply to that object, which means you can do more work with less force. The second way a machine can make work easier is by increasing the distance over which the force can be applied, such as in a lever or using a ramp. Machines can also make work easier by changing the direction that you apply. If you use such things like crowbars, you can push down on a lid and pop it. It's actually applying force in a downward, but the force applying to the lid is in an upward force. So how can it increase the force? So here's an example. A car jack is an example machine that can increase the force or the upward force that you apply to a tire. Not one person in here can lift a car by itself, but by pressing down on the handle, which is a downward force, you're able to move the car up in the air by exerting a greater force upward. However, the distance you push the handle down is greater than the distance the car is being pushed upward, but you have to remember that you do have a greater mass on the car than what you have, so your force is going to be a little different. The jack increases the applied force, but doesn't increase the work being done. So let's talk about force and distance. Work is done by lifting an object, depends on the change of the height of the object. Remember that. If you don't move the object in height, it doesn't move at all, or if you don't move it forward. The same amount of work is done whether you move it or push it, the furniture up or up a long ramp and it lifts up straight up. So, if the work stays the same and the distance is increased, then less force will be needed to do the work, which means you don't have to hurt yourself when you're trying to move furniture. You can use a ramp and push it up the ramp instead of trying to lift it 10 feet in the air. Some machines are able to change the direction the force is applied, such as a wedge-shaped blade is one example, in an axe. The force is being applied onto the handle, and the axe still is able to split the wood. You exert a downward force when you swing the handle of the axe towards the wood, but the blade changes the downward force into a horizontal force, enabling you to split the wood into two separate pieces. When you use machines such as a crowbar, you are also applying a resistance in a different direction. So as you try to pry the lid off of this, your applied force is going in a different direction as the force being exerted by the crowbar onto the box, allowing you to lift the lid of the box and not having to apply as much force as if you were trying to pry it up with your own fingers. Excuse me. You could also use a crowbar to move a large rock. In this case, you would be applying a force against gravity on the weight of the rock. So let's talk about input and output forces. So input and output are the two forces that are involved when we talk about work. The input is the work that you put in, and that is what we know as the input force. This is a force either is being applied by you or something else to that machine. The output force is going to be the force that's put out by the machine that you're actually doing. So on your note cards, if you want to write F subscript N, this stands for your effort force. And again, so let's talk about the output force. This is the output force, is the force applied by the machine, and that is F out. And you can also write that onto your note card as well. So we have two kinds of work that need to be considered when you use a machine. The work being done by you on the machine and the work being done by the machine itself. The work being done by you on the machine is called the input work and is symbolized with W subscript N. Again, you can write this on your note cards. The work being done by the machine is the output work and is abbreviated by W out. And again, you can put that onto your note cards. No, there'll always be work going in and there's work going out. We have to follow the law of conservation. So we're always conserving energy. Remember, conservation of energy states energy cannot be created or destroyed. It can only change from one form to the next. So when you do work on a machine, you're transferring the energy in the machine. So when the machine does work on an object, the energy is also being transferred to the object from the machine, and the amount of energy from the machine, from you to the machine to the object, must be conserved or transferred from one state to the next. It can't just be left there. And this is known as the conservation of energy. Now, this equation can go onto your note cards. The work in is equal to the work out. It must follow the law of conservation of energy, which means your effort force times your distance effort is equal to your force R times your distance R. So now, the force in is the FE is going to be your effort, and the FR is going to be your resistance, and that's going to be done by your work out and your work in. Again, the F times D is the equation for work. So what's an ideal machine? Suppose you have a perfect condition, a perfect machine, there's nothing acting on it, and this includes friction. This means that the work out and the work in would be completely equal. But none of the work in or out would be converted to heat. So for an ideal machine, you would use the equation work in is equal to work out, and it'd be perfect. There wouldn't be any sound energy made, any thermal energy made, any light energy, none of that would be made. It would all go into the machine and out. So, suppose the ideal machine increases the force applied to it. This means that the output force, or F out, is greater than the input force, or F in. Recall that the work is equal to the force times distance. So if the F out is greater than the F in, then the work in and the work out would be equal only in the input force is applied over a greater distance than the output force is exerted over. The ratio for the input force and output force is the mechanical advantage. And there is no label for mechanical advantage, by the way, as we start talking about this. Mechanical advantage of a machine can be calculated from the following equation. Effort force, the force applied to the machine, remember EF, and the resistance force, the force the machine applies, and you get this equation. MA, which is mechanical advantage, is equal to the FR divided by the FE. So you also have to know the force done by the machine over the force that you put into it. The force that you put in should always be greater than the force being put in by the machine. And therefore, the effort, a mechanical advantage, is always going to be less than 1. If the distance if the force is increased. If the distance increases, then it's going to be greater than. It is equal only if the direction is able to change. By the way, you can write that equation onto your note cards as well. Sorry about that. So let's talk about mechanical advantage and talk about window blinds specifically. This diagram is also in your book. The window blinds are a machine that changes the direction of the input force. So the downward pull on the cord, which changes the blind and moves its direction differently. The input and output forces are equal, so the MA is 1. Again, they're changing direction. Note. So, if the mechanical advantage of a machine without friction is called the ideal mechanical advantage, or the IMA. The IMA is calculated by dividing the input distance by the output distance. You can write that onto your, you can write that equation onto your equation card too, along with efficiency. Efficiency is work out over work in times 100%. You're trying to make the most efficient machines possible. Note, in industry, you have to have a high efficiency to have a lower profitability, or you lower your profitability rates. If it takes you a lot of work to make something, but you can't charge a lot for it, you kind of don't make a lot of money off of it. Your efficiency should always be less than 100% because of friction. So, in calculating efficiency, the ideal machine, there is no friction and no output work, and is equal to the input work. So when we're doing some of these problems, we're looking at an ideal machine. So the efficiency of an ideal machine is 100%. The efficiency of a real machine is always less than 100% because you have friction, thermal energy, light energy, sound energy, all these other things that are byproducts. So machines can make it more efficient, and reducing friction usually is done by adding some lubricant such as grease or oil or water. This reduces the amount of surface tension that we have, allowing for things to move past each other easily. And a lubricant will fill the gas within that surfaces and allow for things to slide past. So instead of a static friction, we now have sliding friction. You should remember these terms from the previous chapters. So let's calculate this. So a worker applies an effort force of 20 newtons to an open window with a resistance force of 500 newtons. What is the crowbar's MA, or mechanical advantage? So we're given the effort force, we're given the resistance, we got to find the MA. So now you can pause this and work on these problems. The equation for this is MA is equal to FR divided by FE. Well, we are given both of those, 500 divided by 20. You should have got a mechanical advantage of 25. There is no label for mechanical advantage since both newtons are canceled out. Let's do another problem. Find the effort force needed to lift a 2,000 Newton rock using a jack with a mechanical advantage of 10. So what are we given? Well, we're not given the effort force, but we're given the resistance force of 2,000 newtons and the mechanical advantage of 10. So we need to find the effort force. You can pause the video right now and work through this on your own. So, for the effort force, we use the equation, the resistance force divided by the mechanical advantage. In this case, you would take 2,000 newtons divided by 10, and you would get an effort force of 200 newtons. That is lesson 2. You are going to have lesson 3, and then you can work on some problems.